Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
All right, today we're going to start a two-part lesson, a two-day lesson, where we focus on what a function is and how it is related to work that we've already been doing throughout the year, working with linear two-variable equations. So to start off, let's focus on what is the definition of a function. And so we would say that a function is an equation or a rule in which every input, would be the x values, has exactly one output, which would be the y values. So if you think about this, just think about any of those rules that we've been working on throughout the first semester and that we keep seeing pop up periodically in our homework, maybe like y equals 2x plus 5. This is an example of a function because when I plug in a value for x, say I plug in the number 2, you plug it in here, 2 times 2 is 4, and 4 plus 5 is 9, you would get an output of 9. And so no matter how many times I plug in a 2 here, I'm always going to get the 9 out. And so you would never get any other value here for y other than 9 when x is equal to 2. If I change that to x was equal to 3, I would get 6 plus 5 is 11. And you would never, ever get any other output other than the number 11 there. Let me fix that one. I don't like that. That's much better. So this is an example of a function. And you probably remember hearing me refer to these as linear functions throughout the year without us really fully going into what makes a function a function. This is what makes a function a function. Exactly one output for every input that you put in. And then we're going to work through rules that are written with two variables x and y throughout this lesson. At the end of day 2, I'm going to show you function notation. And function notation is a simpler method of describing a function without a lengthy written explanation. The most frequently used function notation is the f of x, right? So you say it. You don't say f parentheses x. It's really referred to as f of x. And the f of x really means the same thing as y in a linear equation. So you're going to see how if instead of writing it using the slope-intercept form of the equation, we could just say the f of x is equal to 2x plus 5. Or if this had something to do with gardening instead of just some generic rule, I might call it the g of x. Having the g be kind of that little reminder that this rule has something to do with gardening. And so we'd say the g of x is equal to 2x plus 5. So while the f of x is the most common, you could have any letter that precedes this parentheses x, end parentheses. Okay, so once again, we'll get into this toward the end of day 2, and I will also give a brief example or explanation for why mathematicians may choose to use function notation rather than a generic slope-intercept form using x and y. All right, so let's get into it. Throughout this course, you have used rules that relate to variables to make graphs and find information. An example of such a rule is like y equals 5x minus 3. Today, you will look more closely at how rules that relate to variables help establish a relationship between them, that relationship that we have labeled a function. Okay, so your first task here is to draw a sketch of an example of each graph that's described below. Okay, so I've already created these graphs, and what I want you to do is with your graph paper, hopefully you've got your math journal that's got the graph paper in it. If not, get yourselves some graph paper so you can make a nice, clean graph with straight lines and properly scaled axes. And draw what you think would be a good representation of each one of these situations. So the first one is a graph that neither increases nor decreases. I'll underline that. A graph that decreases non-linearly, which means it doesn't form a straight line as it's decreasing. And a graph that increases linearly and then decreases. So it's got to increase for part of it with a straight line and then decrease for part of it with a straight line. And the last one, a graph that is consistently increasing. Okay, so go ahead and I'm going to pause and make sure everything is in order down here. I would like for you to pause and follow these directions. Take about 10 minutes of your time to make those graphs nice and neat, and then label each one of them and make sure that each one of them fits this description. Alrighty, are you ready? Hopefully you've got yours drawn and you're going to compare them to mine. Now, it's highly unlikely that ours are exactly the same, but the basics should be the same. So for instance, a graph that neither increases nor decreases, well, it doesn't go up or down, but it's a graph that must be a horizontal line, like this blue one, right? So as it goes, I don't know what X represents, I don't know what Y represents, but it could be like X is the time of day and Y is the distance away from home, and you fell off your bike and you're stuck in a ditch somewhere not moving, and time continues going on. It's a horrible thought, but that's what this graph could represent. All right, B, what is this one? A graph that decreases non-linearly. So there are different ways you can show that. That is absolutely decreasing, and it is absolutely not a straight line, so that fits the description. You may have chosen to do something more like this. Maybe that's how yours looks. Doesn't really make any difference. As long as it's not a straight line and it's going down as you read it from left to right, you're following these directions. And for C, it says a graph that increases linearly. So we're going to have a line that goes for a while, straight line, and then it reverses order and starts going down for a while. Okay, so that's for C. And the last one was a graph that consistently is increasing. And so for consistently increasing, that makes me think of a slope that's a positive slope, and it's a straight line. So I decided to draw it like this, consistently increasing as you read it from left to right. All right, so now let's go back and take a look at a table. And you may recall us playing the silent board game where you would look at a table of values and you would try and determine the growth rate and figure out starting amount or the y-intercept, and you would create the rule would relate the x and the y values. So go ahead and copy down this table and see if you can figure out what the growth rate is and where the y-intercept is, and then write a rule. And the question that says, is there a relationship between the input and the output values? If so, state the relationship. So basically what you're going to be saying is there a rule that can apply to the situation? If the answer is yes, what is that rule? Go ahead and take some time, copy that down, see if you can figure out what the rule is. Alrighty, so once again, how do we find the rules? First of all, to find the rules, we have to plug in, let me change the color of my pen here. We need to fit into the slope-intercept form, so y equals mx plus b, so we're going to want to figure out what the growth rate is, and we're going to want to figure out what the y-intercept is. Now in this case, the y-intercept is right there, so we know b is going to be equal to 2. So now let's figure out what the growth rate is. So our growth rate is where you take the change in y over the change in x. So going between here, how much does y increase for every time x increases? It looks like x is increasing by 1 every single time. And how much does y increase by? It looks like it's going up by 6, right? Well, this goes up by 1, so does that increase by 6? Yes. Yes, 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 and yes. So in all of these situations, y is increasing by 6 as x increases by 1, which means that the rule is y equals 6x plus 2. So just the fact that we saw that consistent growth rate means that there is a relationship between the input and the output values, defined by this rule right there. All right, so let's start talking about functions. A function works like a machine. Numbers are put into the machine one at a time, and then the rule performs the operations on each input to determine each output. For example, when x is equal to 3 is put into a machine where the rule is y equals 5x minus 7, the rule starts by multiplying your input number 3 times the 5, and then after you get that answer, then you subtract 7, and you would get an output of 8. Okay, so you can clearly see this is what we've been doing all year long. Even a little bit in 7th grade, we were doing that a little bit. So this input and output can be written as an ordered pair as 3, 8, or you can just write it as x equals 3, y equals 8. You can do it that way as well, and it could be plotted on a coordinate graph. Okay, so this brings back memories for me. I used to teach 5th grade. And in 5th grade, we were just introducing students to this relationship between an input and an output variable. And so to get them more engaged, I created this guy, which my fifth graders named Function Bob. They thought it was really, really funny. Notice his math muscles there. So you put in a number here, and it spits out an output pair, and then we record those numbers in a table. So at that point, we were not trying to create rules. We were just looking at how these sorts of things work. And then I would show them that, yeah, we could write this as a rule where this could be X and that could be Y and blah, 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 blah. So I just find it fascinating that CPM, 20 years after I started this with fifth graders, I'm teaching CPM now, and they're talking about a function machine, which is not nearly as cool as mine, still is showing students the exact same thing. All right, so let's answer these questions. It says find the output of the function machine at the right when X is equal to 4. So what I'd like you to do is read through these and pause this. I want you to read through these 3 questions, and I want you to answer them and declare your answers. And then when we're done, then it doesn't tell you to set up a table, but I set up a table of values that can kind of help us kind of estimate what the value for C would be. So go ahead and pause and see if you can figure out these answers. Plug in X into this rule, into this function, in -1 and 10 into this function, and declare what your outputs are. And you could probably write your outputs as an ordered pair, or you could say when X is equal to 4, Y is equal to this amount. I don't really care how you show your outputs. Just we want to make sure we're on the same page and you're getting the same answers. So go ahead and do that. I'm going to pause, you pause, and when you're ready to see the reveals, unpause. All right, so what did we get? When you plug X is equal to 4 into this machine, you get 5 times 4 is 20, and 20 minus 7 gives you 13 for an answer. So this would be the ordered pair that would apply to that situation. When X is 4, Y is 13. When you put in the -1, 5 times -1 is -5, and -5 minus 7 gives you -12. So that would be the ordered pair of -1, -12. And then when X is 10, that becomes 50 minus 7, which is 43. So when X is equal to 10, Y is equal to 43, I wonder what X would be equal to if we worked this in reverse and we told you what the variable was. So if Y is equal to 45, it looks like X is going to have to be some number a little bit more than 10. When X is 11, that becomes 55 minus 7 is 48. So it's got to be a decimal number or a fractional number that's between 10 and 11. So here's where, if you set up a table, sometimes you see those patterns here where, you got your series of input values. I started counting by ones and then jumped to the number 10 so I could solve this one. And then the output values have a counting sequence where, just like the slope ratio, they're increasing by 5 every single time, right? And so that's how you can see that if we go to the 11th one here, that 5 more would give you 48. So our answer for this one has to fall somewhere in between here. 45 is closer to 43 than it is to 48. So it should be closer to 10 than it is to 11. So I'm guessing it's going to be around 10.3 or 10.4. You know what? We don't have to guess that. We can actually solve this using algebra. So if Y is equal to 5x minus 7, and we know that Y is equal to 45, then let's just go ahead and solve for x. So we'll add 7 to each side, and that gives us 52. If 52 is equal to 5x, and that means that 5 times something equals 52. So I'm going to take 52 divided by the 5 and see what that something is. And let's go ahead and use our calculator. 52 divided by 5, and you get 10.4 as your answer, which is what I was thinking. A little bit less than 10.5, should be closer to 10 than 11. So we'll declare our answer when x is equal, when y is, when y is equal to 45, x is equal to 10.4. Okay, so it says here some relationships are special in that they are called functions. Below are 2 relationships, one of which is y equals x squared minus 2 is a function, and the other, x equals y squared minus 2, is not a function. So what makes one of them a function and one of them not a function? That's really the question that we're thinking about. So it says, look at the graph and table of values below for each relationship and discuss with your team why you think the relationship in part A is a function and the one in B is not. And of course, you're watching this video, so you're not with your team. So, I just want you to reflect on this a little bit. Use your ideas to create a definition of a function and be prepared to share your ideas. Okay, well, I've kind of thrown that out because I've already front-loaded the definition of a function. So basically, let's just come down here and see how it works. Okay, so here is y equals x squared minus 2. So your input values, you put them in, and you square the number, which means you multiply it times itself, and you subtract away 2. So this becomes 9 once you square it, right? Because a negative times a negative gives you a positive. 9 minus 2 is 7. Negative 2 times negative 2 is 4, and 4 minus 2 is 2. And then negative 1, when you square it, becomes positive 1, and 1 minus 2 is negative 1. So you see this table of values is now expressed as a U-shaped parabola, which is a non-linear kind of a graph, right? Okay. Here we've got x, and our input value has kind of been changed, right? Because the number that's a part of the expression that is our rule is your input value. When you put this number in and run through the order of operations, you get that output. So the fact that now we've got y squared minus 2 means we've changed our input and output. X is no longer the input, it's now the output. So what we end up getting here is a sideways parabola, right? If you rotated this guy 90 degrees clockwise, now you've got this. So what's the difference between the two? Remember what we said, where we were talking about one input has to have exactly one output. Well, we really want our input to be the x value. So if every x value has exactly one y value, then it's a function. If not, it's not a function. Okay. So in this situation, you got negative 3 gives you 7, negative 2 gives you 2, negative 1 gives you 1, 0 gives you negative 2, 1 gives you negative 1. You never ever have a situation where you have a value for x that gives you a different value for y. And it's okay for negative 1 to give you negative 1 and positive 1 to give you negative 1 because that does follow the rule, right? Every time you put negative 1 into here, you're always going to get negative 1 as an answer. Every time you plug 1 into this function, you're always going to get negative 1 for an answer. You would never plug the 1 in and get a different answer. So this does qualify as a function. Now, I'm sure well, I don't know if you have heard about this. There's something that's called a vertical line test, or sometimes we call it the pencil test. Because you're in class and you're looking at your graph, and the only vertical line you have handy is your pencil. So when you draw this vertical line, or you place it over the top of your graph, if you ever get more than 1 point on that vertical line, and the answer is no. As you're moving this to the right, you're always changing the value for x. And there should only be 1 point from that parabola ever landing on your vertical line. So that's another way of proving that this is indeed a function. Bring this over to here now. Let's start with our values. So here you had 7, gave you negative 3, wonderful. 7 gives you positive 3, that's a problem. Because when you plugged in the value for x, the first time you plugged it into the rule, it gave you one answer, but then the second time you plugged it into the rule, it gave you a different answer. This is what you would consider not a function, okay? So we're established this particular situation definitely is a function. This one definitely is not a function, okay? So now let's look at the vertical line test. This is the only point of this parabola where one value for x gives you one value for y. That's what you call the vertex of the parabola. But as you go across now, notice how when x is equal to negative 1 here, how you get two different values for y. When x was equal to positive 2, you get two different values for y. So that's basically how you tell whether or not a graph is a function or not, by using this vertical line test. And if you've got a table, you look for some of the common values. So here is a 2, and it gave you negative 2, but there it gave you positive 2. So it's not working properly. So I'd like to introduce you to a visual that has always helped my students in the past understand the difference between something that is a function and not, and that is using a soda machine idea. Okay, so whenever you go to a soda machine, you put in your money and then you push a button, right? And the button is like your input value. So if you want a Coke or a cola, you press the cola button, that's your input, and your output is a can of Coke. Every time you press that button, what do you expect to get out? you expect to get a Coke out. Could there be two buttons for cola? Yeah, there could be, right? Here you had one situation where you press this button and you got a -1. Here you press that button, you got a -1. You can press two different input buttons and get the same output. That is allowed. However, if you were to press the button for Sprite and you got a Coke, it's not functioning properly. So that would not be a function. So you can't have two different inputs. Here, one a cola input, here a Sprite input, give you the same output. Or I'm sorry, hold on for a second. You can have that. I'm sorry, I'm messing this up. But when you press the Sprite, you expect the Sprite to come out, right? But if you press it again and the cola comes out, that means it's not working properly. So you can have more than one input giving you the same output, but you can't press the same button over and over again and get different sodas and have this machine be working. Okay? All right. That concludes our introduction to what we're talking about when we're talking about functions. Next lesson is going to go into a little bit more detail, and we're going to present you with some different tables and different graphs, and your job will be to look at that and see whether it's a function or not, and sort of give a one sentence statement as to why it is or is not a function. Okay, so take care. Let's move on to our homework, and then we'll revisit this in our next lesson. Take care. Bye.
Hey, feeling good, like I should.